All right, so I already posted your programming test guide. So please take a look. It's really outlined about the requirements for the test and also the formats. And you will see pretty much the format in 2 practice tests, right? You can check the E-class. Try them out, and then I'll give you the solution maybe a little bit later this week, right? You can also compare the solution as well. And also lab 1 solution, okay? For your lab number 2, it's actually due today. Just submit your best attempt before the deadline. If you still cannot complete it, just make sure you check the solution later and also learn the materials. So for today, since we don't have any in-person, well, we don't have any supervision for tomorrow's lab. I made an announcement yesterday. But Adnan, he will be there in 1002B from 7 to 8 p.m. right after class. If you want to talk to him about the labs, you're more than welcome to, right? You can drop by. Otherwise, you can also email him just for this week about the lab, okay? Alrighty, any question just about the course in general?
When do we expect to release the solution for lab 2?
Lab 2, I would say since it's due tonight, I'll try to release a lab 2 solution either tomorrow, maybe Thursday.
All right,
Let's say before the Thursday class. How about that?
All right,
okay. All right. Okay, so let's do a recap just from last time, and then we'll continue with the relation, right? We'll move a little bit faster today, I'm hoping, but still, we're gonna cover all the math review until next Tuesday, okay? Okay, so last time we just talked about the proper subset, right? I just gave you some connection, back to what you learned in 2101, the data structure course. And then we did some equational style of proof. So I would say this proof over here just demonstrates about whenever you want to argue something. So before you, between every step, you want to make sure you actually, so between these 2 steps, for example, you're going to justify about the theorem. So once we get to the sequence calculus, once we talk about the bridge controller, you will see similar style. Okay, but anyway, just for example. And then we spoke about just different exercises about, just something we went over, right? Quite a variety of things. So I may not repeat, but you can definitely take a look. Okay. And then, I still need to give you the solution, right? I'll do that. Okay, I kind of forgot. So this is just about simple exercises of checking subset versus proper subset. Okay. And, right, so this is very critical. So this page over here just review about the choose operator. So when you say, for example, 5 choose 2, what does it really mean? So it's really, there will be some permutation stage, and also there will be some disregarding the ordering of the sequences stage, right? So we talk about those 2. And we're going to use this formula again today when we talk about power set and also about constructing relation. In some way, relation there, you also have to really use a power set idea. That's something we'll see. Okay? And the n choose I, right? The formula. This is something I'm afraid for your written test, you don't really have any data sheets. So if I do ask you something that has to do with this formula here, you will have to know how to calculate. But later on for the exam, there will be data sheets allowed. You can definitely feel free to put this formula down. But it's not difficult to really remember. But it's more important to understand about how to calculate it. Any question about this formula here? We're going to use it again today, actually. Okay? And we talk about power set, right? So the power set, basically, the definition is the power set of a particular set, right here. We're going to revisit this notation again today when we talk about relations, okay? So when we say a power set of a set, it's basically all the subset of this particular set S. So every member in the power set is another set, basically, okay? And the way to really systematically enumerate it is by considering the cardinality of the each subset. So the subset of cardinality 0, the subset of cardinality 1, and how many are there, right? That's also very important. So because we know that the set itself has 1, 2, and 3 members. Either out of the 3 members, just choose 0. That's basically empty set. There's only one way to construct it. Also 3 choose 1, 3 choose 2, and etc. All right? That's also very important. Okay. Any questions about this? We'll see something very similar about numerating this particular power set because relations in some way can also be defined as power set. That's something we'll see. That's why we're going to talk about power set first. Okay? And of course, about the smallest member and largest member. And just remember this kind of insights. We're going to see something very similar today, okay, very soon. And instead of 2 poles, it's really about cross products. So let's say you got cross product, you can get as many times as you like. So let's say we got a cross product between 1, 2, and 3. is basically going to be a set of pairs or tuples. Each tuple, the size of the tuple correspond to how many sets you are doing the cross product with. So here I'm doing 3 sets right here. That means I got 3 members. The first member comes from the first set, and the second member comes from the second set, and the third member comes from the third set right here. All right, so like this. And I also talk about how you can try to enumerate the set of cross product systematically using a tree. Okay, so that's also something we spoke about. And we kind of stop here, right? So just talk about relation. Let me get back to this a little bit later. I do want to continue with this page, but before that, I want to just review very quickly about the formula about calculating the power set. Okay, just review quickly. So there are basically 2 ways for you to calculate the power set cardinality. So I'm going to talk about both of them. We already learned about one of them last time, but it doesn't hurt to brush up quickly. So let's say what we want to know is this. So we want to know, let's say, the cardinality of the power set of S. So S is any set. All right, let's say that's what we want to know. We want to compute this. So there are 2 ways to compute this. Okay, they are equivalent to each other. Okay, let's see. So we want to calculate this thing over here, right? The cardinality. Okay. So the first way is basically to consider all the subsets. That's approach number 1. By considering the subsets of the various cardinality. That's pretty much what we just recap. Okay, let's review this one quickly. So the first one here is, let me put it here. Because I'm talking about, oh, actually just missing this parenthesis here. Because we are talking about this particular set, so we can say the cardinality of the power set of S will be equal to all the different ways to choosing the subset depending on what's the cardinality. Cardinality should be from 0 all the way to the set itself. So it's going to be cardinality of S choosing 0. Right? That one basically corresponds to empty set. And plus the cardinality of S choosing 1. Plus cardinality of S choosing 2. Plus all the way to the final one should be choosing the maximum subset. Right? Everything together. But of course, the special case would be this one here really corresponds to just the empty set. And this one here also will compute to just 1, and this one will just be 1. This is basically the set S itself, which is also its subset, right? So this formula is good, especially sometimes I may not ask you about just the whole cardinality. I might say, tell me how many subsets are there of certain cardinality. Maybe I'd say, calculate for me all the subset of cardinality 1 and cardinality 2. In which case, only add up these 2 numbers. So you will see one of the example questions I'll give to you for later, the written test. I might ask that way. There's another way to actually compute, which will be to consider whether or not some member should be included. Let me show it to you. Okay, I'll use some example first. Okay, so for this one here, let's see. So let me just write this down first, and then let's just use one example first before we generalize it. Let's say S is simply a set with 3 members, let's say. So let's say S is simply, I'll put it over to the right. S would be, let's say, A, B, and also C. Okay? Let's try to somehow use a binary, like a base 2 numbers to really represent the decision about whether we want to include each member over here. It's more like a binary choice, whether I want to include A or not, whether or not I want to include B, and also whether or not I want to include C. Okay, so let's put it this way. So you're basically going to figure out all the 3 digits binary number. So let's write it now quickly. So we got 0, 0, 0. We got 0, 0, 1, 0, 1, 0, all the way to 1, 1, 1. Right? That's base 2 numbers. How do we interpret this? Oh, first of all, how many do we have right here? 8, right? So this will be 2 to the power of 3, which will be 8 numbers. Right? You can think about each digit here can either be 0 or 1. this digit here can be 0, 1, 2 to the power 3, depending on how many digits you have. Now, how do we interpret that? Think about 0 means we want to include that particular member. Let's say 0 here, that means we want to exclude. Sorry, maybe I said include. I really meant to say exclude. 0 means to exclude, C in this case. And 1 here means we want to include C. Okay, so let's now do some interpretation. 0, 0, 0 means I want to exclude A, B, and C, which correspond to empty set, which is a subset, right? What about this one here? 0, 0, 1. I want to include only C, but I want to exclude A and B. In that case, it will just correspond to just C right here. And finally, if I got 1, 1, 1, that means I want to include everything. That will be A, B, and C. And you can also work out the intermediate numbers, right? So basically, every base 2 number of this certain number of digits is going to correspond to a certain subset, right? That's also another way to systematically enumerate the subsets. Okay, so you can think about the 3 here is really also the cardinality of S, right? You can see the 3 here is really 1, 2, 3, about how many members we have in that particular source set. So we can now generalize it, right? So this one here is basically equal to 2 times 2 times all the way to 2. How many terms do we have? Exactly the cardinality of S, right? And that one there is just equal to 2 to the power of cardinality of S. So we got 2 options here. So we got either option 1 or we got option 2. Okay? Again, option number 1 will be very flexible. You can kind of selectively choose some certain terms to add them up together. And option number 2 is to really consider the whole cardinality. Okay? And I think that there will be some proof that's possible to really show that this equation here is really the same as this one here. You can take it for granted, but we don't really prove it in this course. Right? So these are the 2 interpretations of the formula. You can choose the one that's going to be applicable to you, but just make sure you kind of understand how to interpret them. Questions? All good? All right, think about them, just in case you guys struggle. All right, let's now revisit what we had last time, right? So now we're going to look at relations. And we're definitely going to dive into relational operators, and hopefully we can also talk about functions, which is like a special case for relations today. Let's see. Okay. So let's see what we said last time. The most intuitive way to understand what a relation is to think about a relation is simply a set, and every member in the set is an ordered pair. What should be the size of the pair? Usually should be just 2. That's why we call it a pair, right? So let's say we have a relation on 2 sets, S and T. And then each pair, the first element in the pair should really come from the first set. And the second element in the pair should really come from here. Okay? Another way for you to think about a relation, for example. So relation already right here, it's more like a set. And then I got a pair, X and Y, let's say. So this is the first element in the relation in the pair. This is the second element in the pair. Okay? X should come from S, and also Y should come from T. Right? It's a very simple set comprehension formulation to talk about what a relation is in the most general way. Given this definition here, let's now decide. Just answer some basic questions just to clarify understanding. Is 1A a relation? We said no. Even though 1 comes from here and A comes from here. However, this is a single pair. It's not even a set. So it's not a relation. Right? As simple as that. On the other hand, I can write down something to fix it right away. Is a singleton set 1A a relation on S and T? Is it a relation? Yes, indeed, because now it is a set. And the relation has only 1 pair, which is completely fine. It's a set of pair, which can be empty as well, right? So this one here, yes. Okay. All right, another simple one here. is B2 a relation on SNT? What's wrong with this? It's a set, a pair. The order, right? Remember we said it's an order pair. So this B here does not come from here, and 2 here does not come from here, right? So that's why it's no. The order is wrong. Okay, for example, here, B here is not a member of S. And also 2 here is not a member of T, right? So really the order got to be right. Question?
So you're saying the English expression of S and T is not commutative?
It's not. Well, I wouldn't use the word commutative over here because we just talk about, whenever we talk about relation, the order really matters about which set should be really come from. Well, we're going to see that S is really where the domain set will be based on, and T is going to be where the range set will be based on. We'll see that. But just the order really matters.
So based on the English expression, the S should come from up.
Yeah.
From the T. Okay.
Yeah, S should really come before T. So the order really matters. Okay. Also, you can see the definition here, right? You can see that we say each pair is X and Y. X must be a member of S, which is the first set, and Y must be a member from the second set, right? So the order really matters. Of course, there might be some special case where maybe S and T are exactly the same. It doesn't really, it's also fine. You can also say maybe a relation is also acceptable. I might say a relation on maybe S and S. So this is also acceptable. So that simply means I got 1, 2, 3 as the first element. And also 1, 2, 3 also can be the set for the second element. It's definitely fine as well. Okay? So this is also acceptable. Okay? And for your lab number 2, right? So once I release the solution, we can go over parts of it for lab number 2, maybe on Thursday or maybe on next Tuesday. Maybe Thursday will be better. We can do that. So there's a relation there called ID, identity relation. The way to define that is by using this. You can think about it, but I can go over that maybe a bit on Thursday. Okay? Okay, you can think about another relation here, which is an ID relation, identity. All right? Okay, one more. What about this one here? I think that's good enough, okay? So the order, because it's a set, so the order doesn't really matter. So if you say R1 is, let's say 1A, and then 3B, and then R2 over here, you just say swap the order. So you might say 3B, and then 1A. Since these two are the same set, disregarding the ordering, so they are really considered as the same relation. R1 over here is equal to R2. Okay, one more check right here. Okay, put it here. Given that we got S and T, right? What is the minimum relation on S and T? Think about it. And then also, what is the maximum relation on S and T? So each one of them should be a set, basically, right? So we talk about maximum right here, and also minimum. The minimum relation might be quite easy to see, right? What's the minimum? Empty set, because a relation is a set of pairs. What's the smallest set possible? Empty, right? So empty set is considered a relation called an empty relation, all right? What about the max relation on S and T? Cartesian product, exactly, right? So S cross products T. All right? S cross product T is going to give you, for example, 1A as a pair, 1B, and then 2A, 2B, 3A, and 3B, right? Give you all the possibility. Okay, that's a cross product. So guys, these two insights are very, very important because the way we're going to systematically enumerate about all the relations is based on this observation here. So everything in between should be done in a systematic way. Okay. Good. Any questions? Go ahead.
Would there be any set where the minimum relation is not the empty set?
So say it again?
Would there be any two sets where the minimum relation is not null?
No, actually, because by definition, the relation is just a set of ordered pairs. So the minimum will be just empty set. Yeah, always. Yeah. And also, always the maximum would just be S cross product T. Okay. Awesome. And then, all right, let's now talk more about the notation here. Okay. So just go over one by one. Okay, right here. All right, we see 3 bullet points here. Let's go one by one. Now, this is very important. How do we express the set of all possible relations on S and T? We know that this is a single relation, that's a minimum. This is another single relation, that's the maximum. How do we somehow use a notation there to express the set of all possible relations?
Power set.
Power set, I like it. We definitely need power set. That's
S cross T.
power set of S cross product T. All right, that's actually right, but let's see. So this is the notation. We want to get a power set of S cross product T. But let's try to understand why this makes sense. As we said earlier, S cross product T is a maximum relation. Given that it's a maximum relation, any subset of it is a set of pairs. That should be itself another relation, okay, including the empty set. So the power set over here is basically going to be the subsets of the maximum relation. Each one of them is going to be a subset, and each subset is going to be itself a relation. So you kind of collect them all together. So the way to understand about this expression here, think about S cross product T. That's a maximum relation you can get. And then every subset of it is going to be just a relation itself. Okay? What about we do a little bit, we'll do that, some example right here. Oh, how about we just do this one here? Let's now let's give you some idea quickly. Let's say this is S and this is T. Right? The maximum relation on this one here will be basically the cross product, which will be size 4. Agree? So we basically got A2 and also A4, also B2, and also B4. Right? It's a set. 1, 2, 3, 4. So this one here is really the cross product, first of all. Let me do a little bit better. So this one here is really the cross product. S cross product T. How do we understand about the power set over here? So we're going to try to figure out exactly what are the possible subsets of this. For example, the subset might contain just this single pair. In that case, it's one relation. It might contain only this single pair. That's also one relation. It might contain these two pairs. It's one subset, which corresponds to one relation, etc. Right? Okay, so this guy here, there's another way to write it, which is like a symbol you will see also. Maybe you have already used it, maybe in Rodin. Okay? It will be S double arrow, cross and T. So one thing you want to somehow remember, they are synonym to each other. So when you say S relation T, this is really the same as the power set of S cross product T. They're the same. Of course, this one here doesn't tell you much about how we figure out the set of relations, but this one does. All right? Okay, and then let's see. Okay, this one's done. And how do we say R, which is a set, is a single relation? If there's a single relation, it's simply just a member of the set of all possible relations, right? Just a member, okay? So you can either say that R, right, is a set. You can say R is a member of the power set of S cross product T. Or you can say R is a member of S relation T. You can say either way. Okay? Of course, in rodent, you would just say colon, right? That's really how you do it. All right, any questions so far? We good? All right, so now the job is to enumerate all the relations between A, B, and 2, 4, right? So let's see how we do that. And also got to figure out exactly how many. Oh, actually, how many might be something you can already answer, right? Guys, how many?
16.
I heard 16, okay. Would you guys agree? Okay, so remember one formula there is to calculate the 2 to the power of S. And the S right here inside the power set is the cross products between S and T. What's the size of the cross product between that particular example, right? So I'll put it down here. So this one here is going to be 2 to the power of S cross product T, which will be 2 to the power of, right? You can see 2 here and also 2 here, right? If you like, I can say 2 times 2. 2 to the 4, great, 16. So we know that if I want you to enumerate exactly all the relations in this set of all relations, it's going to be 16 members. Okay, let's see. So let's now try to enumerate them. Not all of them, but I'll give you the idea. Overall, it's going to be a set right here, right? It's a big set. Every member in this set is going to be another set. And that set represents a relation. Okay? And we're going to do in a very similar way about how we enumerate about the like a power set, right? So we start with the minimum relation. Okay? You can think about this is the relation of cardinality 0. Okay? And the maximum should be basically the cross product, right? Which will be, let me just write it down. So you got A2, you got A4, well, exactly what I just enumerated here, right? I'll just repeat them. And then we got B2, and also we got B4. Okay? So this is a relation of cardinality 4. That's a maximum you can get. So what's really missing is about the relations of cardinality 1, cardinality 2, and cardinality 3. We are missing those 3 categories. Okay? I can just do one of them. How about that? So let's say we want to enumerate the relations, let's say in the second row. We want to enumerate all the relations of cardinality 1. That means each member there should be a set of only cardinality 1. Would you agree? One of them should be just one member, A2. Be careful here. You got to say a pair, A2. You can see it's a set with just one pair inside, right? Just containing just this one here. And the second one will be containing this one here. Okay, write it down. So we got also A4. Also we got B2, B4. Okay. How many do we have right here? Because the 1, 2, 3, 4. How does that correspond to the choose operator? right? Because we know that the maximum relation has size 4. And S cross product T has the size 4. So you can think about this one really correspond to 4 choose 1. Right? Out of the 4 pairs in the maximum relation, we want to choose just 1 and make a relation out of it. And this one corresponds to 4 choose 0, which is just 1. There's only one way to choose a relation of cardinalities 0. And this one here will be 4 choose 4. Okay? So finally, you can, okay, for the other two, I'm going to let you do it. Okay? So we got one here. Relations of cardinality 2 and also relations of cardinality 3. You're going to put them all together. Relations of cardinality 3. Okay, this one here can be 4 choose 2, and this one 4 choose 3. If you add them up together, it's going to be 16. Okay? Could be a little bit tedious exercise, but you got to be very patient, also systematic about doing this. Okay? Okay. All right, any question about enumerating the relations and also calculating the size? Okay? If that's good, let's see. Okay? I do have another little exercise for you. I'll write it down. Okay? And we can do some of them right here. Okay. Exercise. So let's say we got 2 sets. We got departure, like a cities. And we got another one called destination. Okay, I'll just put some cities here. Let's say Toronto, and then Montreal, and Vancouver. That's all Canadian cities. And then put some international cities here. How about Beijing, for example, and Seoul, and also Penang. Do you guys know where it is? It's in Malaysia. Anyway, doesn't matter, right? You can choose your city right here, okay? So anyway, so we got departure and destination. And now, let's create a relation. I'm saying that airline is a single relation. How do I express that? It's a member of a relation between departure and destination. Departure and destination. Of course, I'm already using just a shorthand for a relation, but just rewrite it once more, okay? So this one here is really equivalent to the power set of departure cross products, oh, actually they're both D. Departure cross product destination. All right, like that. They are equivalent. Okay. So I got 2 questions for you. Number 1. Okay. What is the cardinality for the whole relation? Oh, let me write it formally. What is the cardinality of departure, relation, destination? You don't need to tell me the concrete number. That's okay. You can calculate it, during the test. That's okay. But how should we express that? It should be 2 to the power of something, right? What should be the exponent? 3 times 3, the size of the cross product, right? It's going to be the size of the departure cross products destination, which will be 2, and each one of them is 3 and 3, right? So 3 times 3, 2 to the 9, 5, 12. So any numbers I might give you to calculate, it should be not too large, don't worry, in the test, but I don't think you really need a calculator. I'm pretty sure you can calculate this, right, by hands. Okay, and then, of course, in theory, you can try to enumerate all the 512, but don't do it, okay? I'm pretty sure you won't do it. But I can maybe do something like this. I might say enumerate those relation with cardinality 2. Now, let's do a little bit of exercise here. Those relations with cardinality 2, what do I mean exactly? Okay, those relations with cardinality 2. Okay, let's now think about this one here. Okay. Yeah, basically let me formulate it for you. Okay, I'm basically saying I'm considering the set of all possible relations between departure and destination. These are the all set of possible relations. I want to only get those relations of cardinality 2. Okay? First of all, before we calculate a number, we want to know how to understand this one formally using set comprehension. Okay? It's going to be a set right here. All right? And then it's going to be some relation R, right? This part is easy. But now we want to put a constraint on the right-hand side. Okay? First of all, that should be a relation between departure and destination. Right? It's a relation. And the cardinality of R is exactly equal to 2. Right? That's a very precise meaning about what I really mean by R. Okay, so if you want to enumerate this, how many do you need to enumerate? How many? Yeah, because that one there basically is going to be some choose operator, and we know the maximum relation is really the cross product between these two, right? So you can think about this one here. It's going to be the departure cross products destination, right? The cardinality, and choose 2. And we know that this one here is actually 9. Right? 9 choose 2. You can apply the formula. I'll give you the number. You can verify by yourself. That one there is simply equal to 36. So 36 is not big. It's okay, right? But if I do let you enumerate that, for example, in the exam, that should be considered like an easy question, right? Because you just need to do the work to actually enumerate it, or something smaller, okay? Okay, so that's kind of exercise here. You know, we can do it all together. All good, okay? Why don't we just do one set of relational operators, and then we take a short break, right? So now we're done with all the definition for relations, and now we are able to just introduce different operators. Okay, we're about halfway. Okay, why don't we just do one set, and then we take a short break. Okay, so if you see the slides, let me show you very quickly, right? I may not follow exactly just read off the slide. I just want to show you what you should do, right? So this is something we have talked about so far in today's class, right? And that's really about numeration that we did. Okay. So for each individual relational operator, I will do some example together. And you can see that, for example, when we talk about domain, each operator, I will also give you the formal definition about what that relational operator really means. And the way to check its precise definition to really define that precisely is use a set comprehension. So you will see lots of examples for set comprehension. So definitely take advantage of all these expressions there in the slides and try to make sure you make sense out of them. Okay? But let's now just go up to domain. Okay? You can look at the formal definition, but let's now just do some example here. Okay? So you can think about R here, just individual relation. I said R is simply a single relation, right? It's a set of pairs. You can think about it, some implicit declaration there. I simply say R is a member of, because we talk about like A, B, C, D, etc., like an alphabet, right? You can think about there might be a carrier set called alphabet. Alphabet and relation, and then integer. Okay? So this is the implicit declaration we have, right? So R is just a single relation. Okay? And let's talk about domain, range, and inverse. And we'll do a little bit of algebraic properties, which will be the exercise. Okay? So let's start with domain. Domain of R. You just pick the first element for every pair in the relation. So it'll be A, B, C, D, E, F, right? And make a set out of them without any duplicates. So that would simply be A, B, C, D, E, and F. That's a domain. Basically, all the first elements combined together without duplicates, and ordering doesn't matter. Range will be the second elements altogether. So the range of R will be 1, 2, 3, 4, 5, 6. 1, 2, 3 altogether. So it's going to be 1 to 6. 1, 2, 3, 4, 5, 6. And one very important point to say. So here, the domain of R, in general, should be just a subset of the first set over here, alphabet. Does not need to cover the entire alphabets for a single relation. Does not need to. Alphabet. Also, the range of R will just need to be a subset of integer. Also, does not need to cover all the integers. Okay. And inverse. Inverse simply means I'm still going to get a set of all pairs, except the first and second elements swap the order. So swap the order, swap the order, swap the order, etc. Okay, let's write it down. So on paper, R tilde is a superscript. All right? And I believe in Rodin, please double check, I believe. Something like that, but without a superscript. Okay, double check. Okay? So you might need that actually for your programming test, I can tell you. You might need that. Okay, right here. So that one there is going to be, for example, A1 is going to be 1A. B2 is going to be 2B. C3 will be 3C. And then we got 4A. And then we got 5B. We got 6C. And we got 1D. And we got 2E. And we got 3F, right? Very straightforward. The cardinality is the same, right? You can also look at the set comprehension notation there to see the definition. All right, this exercise here, basically we want to consider R and also its inverse, which will be R inverse right here. How do you relate the domain of R and range of R to the domain of R inverse and also range of R inverse? For example, anybody who want to? Diego.
So for the inverse, the domain of the original relation becomes range, and then the range of the original relation.
Yeah, okay, exactly. Okay, let's see this example here. Domain is right here, right? Domain of R. A, B, C, D, E, F. And the range of the inverse will be A, B, C, D, E. Exactly the same, right? So we're going to say the following. We're going to say the domain of R will be just the range of R inverse. Because by definition, the inverse will just switch the order of the two elements, domain to range, range to domain. Similarly, we say that the range of R will be just the domain of the R inverse. Right? So these are so-called algebraic properties. And we'll see a few more later, just to help us understand a little bit more about how the different relational operators can be combined together. Algebraic properties. I'm pretty sure in your linear algebra class, you actually have seen something like that, right? Similar flavor. Okay. So I would say domain, range, and inverse are the most basic operator to understand first. And then we'll take a very short break. After that, we'll actually talk about other operators. All right, so please get your iClicker ready, and we'll take a short break. All right, so before the break, we cover up to domain, range, and inverse. All right, let's now talk about image. Okay, image is actually also very useful operation. It's not too difficult. Okay, let's see exactly what it is like. Okay. Oh, by the way, for every relational operator, you will see that not only that I give you the definition, but also you will see the rodent syntax as well. Okay, it's actually rodent syntax. You can also take advantage of that, right? So it's going to be a very good study reference for you. All right, let's see exactly how we understand the image. We'll see by definition here. Okay, let's see, just calculate some example, and we'll see. Okay, whenever you want to calculate the image on a relation, okay, image of some set of a relation. So let's say here, if I say I want to calculate this one here, okay, this is okay for me to calculate, right? I'll talk about something that's not okay, but let's calculate this one first. The way to write it is, I have this relation here, right? The R is right here. Square brackets, a little bit like an array indexing notation, okay? And here is going to be a set. And presumably, the set should be a subset of the domain of the relation. It should be. Okay? Okay? So, oh, you know what? Let me say one thing here. So if you remember over here, so R here is a member of the relation between alphabet and integer, right? Alphabets and integer. Okay, I beg your pardon. I said something wrong here. I'll fix it. In order for us to really, in order for us to calculate this one here, sorry about that. In order to calculate this one here, we got to make sure the set we pass over here is something that's valid. It's got to be some alphabets for us to calculate. All right, so it has to be alphabets. It must be alphabets. So the alphabet is really the first set that we have over here. Doesn't need to be the domain of R. I'll give you another example in just one moment, right? It's really important to see the distinction. So here, I simply say, let's say A and B. Okay? So this here must be a set. If you simply say, let's just say, rather than a set, you just say it's just A. It's wrong. However, you can say it's a set containing just A. That'll be okay. Right? So typing-wise, this middle thing here must be exactly just one set. Okay? It cannot be a single member. So by definition, it is like this. It's going to be all the R prime, all the range value, basically, such that it's going to give you some range values from the relation R. We know that D and R prime is a member of R. What does that mean? So remember, relation is a set of pairs. So we're talking about every pair. So you can think about D here, R prime here can be A1, or can be B2. So A here can be the D, 1 here can be the R prime. Or alternatively, B here can be the D, and 2 here can be the R prime, etc. Right? We consider all the pair. What should be satisfied? Since we're calculating the image of just AB, so we want to find all those pairs where domain value here is a member in AB. All right? So that one there is saying D should be a member of AB. Yeah, the domain value. D here and D here. If the domain value will match, then we collect all the R prime. Okay? So now since we got AB, right? So let's see. So let's find out all the pair that involve A and B. So A, B, That's it. But we don't collect a whole pair. We collect just the second elements. So we only collect 1, 2, 4, and 5. 1, 2, 4, and 5. The answer here always is a subset of the range of R. All right? And let me make a clear distinction right away. Okay? Here, can we say S should always be a subset of the range of R? Which means it should always be either A or B or C or D or E or F. It doesn't need to be. Okay? Let me show you some example. Okay? Not necessary. Okay? Let me show you this. Let me give you the extreme case. If I say R, and then I would say G. This one here is valid to write because this one here is a subset of the alphabets. But it does not contain any domain value. Now, what should be the image here? Right? You're basically asking, what would be the set of range value that's mapped by G? Do you have any first element here being G? You don't. So it's going to be just empty set. So this one here would just be empty. And the way to interpret that is there's no value mapped from G in R. Yeah.
So for the S is a subset range. Do you mean domain or do you mean range?
It does not need to be, oh, I really meant domain. Thank you. I really meant that. It's a typo. It's definitely wrong. Okay? It doesn't need to be the domain. Okay? Apparently, you can see this one here. G here is not in the domain, right? So it's okay. You can still compute it, it's just empty. How about do one more, all right? How about we got R here. And then I would say here, A, H. What would this be? You basically want to find all the range value that's mapped by either A or H. What are the pairs mapped by A? This one here, and that's it, right? Is there any pair mapped by H? Nothing. So only these two will be collected. Okay? Another way to think about it is, it's really like a R mapped by A. Union R mapped by H. And this one here is totally just empty. And this one here is just going to give you two. Just A1 and also A4. Okay? A1 and also A4. All right, so the answer for this one here would be just this set of pairs. Okay? You can think about we're trying to map individually from the image over here, A and B, and then collect them together by union. Okay, all good. Let's now try a little bit more to check. Okay, how about this one here? I say I want to find. Let me just write it down. If I say here, R image of 1 and 2. What is that?
Syntax error.
Syntax error? Not exactly syntax error. Syntax error like you misspell certain operator, right? It's not really syntax error.
Not acceptable.
Not acceptable, or maybe like compilation error. Like this is simply undefined. Because this one here, you can see, this is not a subset of the alphabets. Because here, every element here should be the first set alphabet, but it's not. So it's undefined. Okay? Not empty set, by the way. It's not. It's different, right? So that's why you want to make a clear distinction. One moment. I'll write it down first, and I'll answer your question. So this is undefined. Question? Yeah.
And that should be just 1 and 4. Do we have to still write the whole set for the
So say it again. Which one?
on the top, it says image of A and H. It should be just 1 and 4 for the range, right?
Yes, that's correct. Just 1 and 4. Yes, I agree. Yeah, again, again. Sorry, that's also another mistake made by me. Thank you so much. 1 and 4. Because it should be a subset of the range. Thank you. Yeah. Good. And now, is this okay though? Right, because we take the inverse, right? Okay, so let's now also write it down. So now if you say R inverse, and then I'm taking 1 and 2. Okay, I'm going to write down the value. You guys can double check, right? It's going to be A, B, C, D. Right, you can double check. Okay. And we got 2 algebraic property for you here. Okay. 1 here, and also 1 here. Okay. Basically, we want to use the image operator, the square brackets over here, use that to calculate the range and the domain. This one here might be a little bit easier. Okay. Diego, go ahead.
Sorry, quick question for the
Yeah.
statement you just wrote, the R inverse of 1 and 2,
Mhm.
would that be A, B, D, and E?
So let's see 1 and 2. So we get 1, 2, and also 1, 2. We got A, B, D, and E. A, B? Yeah, actually I do have A, B, D, and E in my notes. I'm not sure why I put it wrong. Thank you.
And then my second question was, so the R prime on the definition just starts for as an element, right? Like that would be
So which definition?
for the element, for the R prime on the definition, the blue statement.
This one here.
Yeah.
Yeah, the reason that I didn't really choose the R over here, if I choose R, you can see I got R and R here. I got clashes. Right?
It could be, for example, like an X.
Yeah, exactly. It's more like a dummy variable in some way, right? You can maybe choose, if you like, you can say X, and then you put X over here. It's definitely fine. It's just a way to make sure you don't really choose anything that will clash with the relation name. That's why.
So the answer is basically just a set of elements.
That's correct. Yeah, it's going to be a set of elements, and this element here must be the second element in the pair, right? Good. All right, so for this one here, how do we somehow express the range using image? Okay, so I'll start you with, I can say R here, and then I want to put something inside, and then I will actually end up getting the range of R. What should I pass inside here?
The domain of R.
Domain of R? Domain of R? Yeah, that one's easy. Okay. How do I also use the image? But somehow I want to calculate domain rather than range. Basically, what I want to get is somehow I want to put something here, and then I want to get the domain of R. What should I pass over here? As the relation here, and also as the image set over here. Yeah?
R inverse range.
Yeah, you guys are good. Okay, these are just something for you to think about, right? If you're not thinking that fast, that's okay. Just think about these properties, okay? So we got R inverse, and then you can say the range of R. Alternatively, this part over here, you can also say it's the domain of R inverse. You can also say that, right? Think about all these kind of different combinations, right? I think that the algebraic properties are really nice for you to just understand a little bit more about how things work together. Okay, image. All right, the next one, okay? The next one we got domain, we got restriction and subtraction. Let me talk about all four of them. Okay. Okay, let's see. So let's make some assumption here. So let's say we got some relation R, a member of the relation between S and T. Okay? And then we got little s, lower s. It's a subset of the first set, S. And also little t is a subset of the second set. Okay? So just don't get confused. You can think about we got S here, S here. We got T here. Also, we got T here. All right? That's our assumption. Given these, let's now try to define four operators. Okay, talk about all four together. I'll give you the paper version, but you can look up how to write them in ASCII sign. Okay, in Rodin. Okay, so let's put a table here. So we actually got right here. So let's say restriction, also subtraction. Restriction and also subtraction. And also we got domain and also range. You will see the full definition also on the slides, but I'll just talk about symbols first. Okay? So there are four operators here. We can either say domain restriction, domain subtraction, or we can say range restriction or range subtraction, right? We've got four operators in total. Okay? First of all, let's understand the symbol. Okay? In the case of the domain, the little s, the set, is going to appear on the left-hand side because you can think about domain as like a left set. Okay? So I'm going to put the little s right here and right here. And the relation R is going to appear right here. So S is like a domain of R, so that's why it appear to the left of R. Okay? And restriction will go like this. You will point to the domain set right here, like a triangle, but pointing to the domain set. And subtraction is just going to be like the same symbol, but I put a minus inside. Minus. Okay? So that's the domain restriction, that's domain subtraction. Okay? And similarly, in the case of the range, we're going to put a little t here to the right of the relation. Okay? So we're going to put the t here and t here, R and R. Okay? Right here, pointing to the range set. And then in the case of subtraction, we put it like that. So you can think about like this. That's for the domain, and that's for the range. And it is very important to know that each operator is actually going to give you a new relation. Going to be a new relation. Okay? Each of these operators returns or evaluates to, returns a new relation. Okay, let's just take one of them as an example. Okay, so let's say I take how about this one here, domain restriction. Okay, I'm just gonna put down its definition here, and we'll see. By definition, if I say I got some little s or little s, that's okay. S and then R, we say R domain restricted to little s, okay, the set S. And then by definition, it's going to be a new relation. And each pair is going to be D and also R prime, such that, okay, so now we got to define what D is and what R prime is. So first of all, D R prime is in the original relation. So R here and also R here, right? It should be there. But we are restricting the D to only certain value. And the value we are restricting D into is from this little s. Okay? So we're going to say that one there, and the D here should be a member of little s. You will see similar definition on the slides as well. But the main point I want to show to you is, as you can see, it's going to be a set of pairs. So after applying domain restriction, you still get a relation. Okay? But in the image that we talked about before, it's a set that we're given, right? Not a relation. Okay, so this one here is basically still a relation. All right, any question here? Just a summary about the operators. Okay, and then let's now do example about all these four. They are very intuitive, right? So we can do it all in one go. Okay, so we are basically talking about the same relation right here. Okay, and let's say the little s we're talking about is AB. Okay, we're going to talk about the same relation, domain restricted to this, or domain subtracted to this, and etc. Okay, let's talk about each one of them. The first one, if I say R domain restricted to AB, what that means is I'm going to somehow filter, I'm going to select all the pairs where the first elements is going to match either A or B. Okay, I got this one here, I got this one here, I got this one here, right? You can see the very first element there is AB, AB, right? So this is going to return back to us a new relation, collecting all the satisfying pairs, where the first element is a member of A and B. Okay. So we got A1, B2, also A4, also B5. So this is a new relation. Let's compare, contrast right away. What if I say domain subtraction? If I say here, R domain subtracted AB, we're doing the opposite. Any pair that satisfy where the first element is either A or B, we get rid of them. Okay? So get rid of this, get rid of this, get rid of this, get rid of this, and this one here. You can see A, B, also A, B. We don't want them. And then collect the rest. It's going to be C3, and also C6, and also D1, and also E2, and also F3. Like that. Okay, that's a domain subtraction. Okay, let's do range restriction and subtraction as well, just for completeness. Very similar idea. Okay, so let's do range restriction. R range restricted to. So now I should put some range value, right? So like a second set value, like a numbers. I might say 1, 2, for example. Now I want to restrict to just 1 and 2. Okay. So any one of them is actually 1 and 2. 1, 2, and also 1, 2, right? So all these pairs should be collected. 1, 2, and 1, 2. Like that. So we're going to get A1, and also B2, and also D1, and also E2. Okay, range restriction. Let's do final one. What about range subtraction? So R, range subtracted by 1 and 2. 1, 2, and also 1, 2. You want to get rid of them. And the rest, right? The remaining one. Collect them. So that'd be C3, A4, B5, C6, and then F3. All right, so these are all the 4 operators you have. right? Just make sure you know how to compute them, right? So I might just give you like different ones, right? All right, any question? Of course, the best way for you to really study for this is also to really convince yourself the formal definition actually makes sense. All right? Okay. Okay, we've got about 5 minutes. I think we can do quickly part of the next operator, which is overriding. Okay. Okay, so let's now do the next one. Okay, the overriding operator. So there are two ways to really understand this operator. For today, just about 5 minutes, I'll just give you the definition first. And then let's understand what the definition is saying. And then maybe you can think about it in the next 2 days. When we come back on Thursday, I can give you a little bit more intuitive interpretation of that. Let's take a look. Again, we got some relation, okay? And the symbol you have goes like this. I have the relation here. And then I want to say overridden by, so it's a triangle, this way. It's a triangle like this, a little bit like a domain restriction here, but I'm going to say the minus here. And notice that the horizontal bar here doesn't go like this, because this way that'll be domain subtraction, right? You want to go just like this. Okay? And then I got T. So R is a relation. T is also a relation. Both are relations. So R here is a relation. And T here is also a relation. And this will be equal to, by definition. Let's go over the definition very quickly, get an idea, and then that'll be it for today. Okay, we'll do an example next time. So this will be, by definition, like this. It's going to be a relation overall. So it's going to be a set of pairs. The pair has the first element D and second element R prime. So you can see this will be some kind of like a domain value. This will be like a range value. But let's now define the constraint. So there are two parts for the overriding, two parts. The first part is actually very easy to understand. The first part is saying the D and R prime must be a member of the second relation here. So the T here and the T here. That means T itself will be included in the actual overriding. Okay? And then we're going to put some disjunction here. Disjunction simply means I'm going to include D and R prime, either because this condition is satisfied or this condition is satisfied. Either way. Let's see the second condition. The second condition is saying this. I can keep all the pairs in R only if the domain value is not in the domain of T domain. Okay, let's write it down and then we'll see. So this part here is slightly more complicated. Okay? D and R prime is in R, that's okay, in the first relation. R here and R here. However, it is required that the D here is not in the domain of T. So this is the T. Okay? That's the definition. Let's now try to break it down. Okay? Since we got union, that means we consider these two sets separately. We're going to union them together. Let's put it first. Okay? Set some foundation also for Thursday. So it's going to be union of two sets. It's going to be dr prime such that dr prime is a member of T. Union, right? I turn this disjunction into union. And also D R prime such that. So D R prime is a member of R. And also D is not a member of the domain of T. Like that. Okay, it's a union. Right, try to maybe take a look at how each one of them is going to correspond to the what relation. Right, take a look at that, and then we'll continue from Thursday from here. All right, thank you. I'll see you on Thursday.